delivered by Paulo Teixeira, and the title is Liquid Crystal Foam. Please, Paulo, the floor is yours.
All right. Thank you, Epifanio, and thanks to everybody for being here. I'm going to talk to you today about liquid crystal foam. This is some work I did a few years ago with some experimental friends who actually did most of the work. I did very little of what I'm going to show you. And this is a lot of people, and mostly an experimental group from the material science department at one of Lisbon's universities. And I'm taking a very calculated risk in doing this because first I didn't do most of the work, and second it's experimental work. So let's see how it goes, how well I can manage this. We'll see. Right, so at this point these friends were playing with room temperature ionic liquids, although I don't really think the results I'm going to show you are crucially dependent on the fact they're ionic liquids. What is crucial here is that these are room temperature ionic liquids which have some liquid crystalline phases. They are crystals at low temperatures around, well, depending on exactly which compound they use, around either 50 or 70 degrees they go smectic, and at higher still temperatures but below 100 degrees C they go isotropic liquids. Okay, so just a few words on room temperature ionic liquids. First, what they are. They're basically salts whose melting point is somewhat conventionally defined to be below 100 degrees C. This contrasts with the usual molten salts like sodium chloride, cesium chloride, etc., which have melting points in the thousands of degree range. And typically these room temperature ionic liquids are made up of large polyatomic ions, including carbon chains. One of the reasons why people are interested in them is that because they have they're ionic liquids, but they have low boiling points, they have some interesting potential applications, such as green solvents for industrial processes, conductive matrices for electrochemical devices, and a few other fun things. And also by careful molecular design, they can be made to exhibit liquid crystalline phases. These are smectic or columnar type liquid crystalline phases at or near room temperature, as I've just described. And these phases have enhanced ionic conductivity, although this will not really preoccupy us here. So my friends were playing with these compounds. This is what they look like. I'm going to try and say that N-alkylimidazolium. So I managed, not too bad. And what do? You dissolve them in acetone and then you precipitate them. Okay, so this is what they look like, and there's two different compounds depending on the size of that alkyl chain there. It can be either 8 carbons in length or 10 carbons in length. Okay, that's the cation, that's the anion, and these are both large polyatomic ions. And then what did they do to them? Basically, my friend's student wanted to look at these under a microscope. So she prepared a microscope slide, and of course when you prepare a microscope slide, what do? You precipitate the stuff onto the bottom slide, you put another piece of glass on top, and then, well, you press on it a bit. So effectively you shear it. Well, at room temperature, this was all done at room temperature. At room temperature, what she got should be a solid, a crystal. But when she looked at it under the microscope, what she saw was that. Okay, so these are textures which are typical of liquid crystals at room temperature where they should not be. So somehow the shearing melted them, and what we get is this very nice smectic-like textures, a mosaic texture for compound 1A, and some focal conics for compound 1b? Well, it so happens that these are fairly weak solids made up of stackings of long chains. So maybe just shearing them is enough to, quote unquote, melt them into the smectic phase. But it turns out that they can survive in that state for at least 1 day or maybe longer. So we believe this is a non-equilibrium state, but a rather long-lived one. Well, this is not all, because it gets even more interesting. If you prepare them in the right way, what you see under the microscope is something like this. That is, they look like a 2D foam. We're talking films of 10 to 20 microns thickness, and because of the chemical nature of these compounds, remember this is a sandwich of a liquid crystal film between 2 glass plates, and anchoring at the plates is homeotropic. What we're looking at is a picture between crossed polarizers, so there is optical activity going on here. The scale bar here tells you the typical length scale of the pattern. This is a relatively early time pattern that is tens of minutes after it was first prepared. We'll look at time evolution in a moment. So you see that there are, well, regions. Space is partitioned into regions which I shall interchangeably call cells or bubbles, and basically this looks like a foam. This looks very much like a... This is, we sheared it and then we stopped. We left it to itself. Okay, we'll look at an experiment under controlled shear a little later. But this is uncontrolled shear. Basically, we made it and then left it to its own devices.
Isotropic solution or what? Before you add acetone, but you said you precipitate.
Oh yeah, what you do is you take that compound which is a crystal at room temperature, you dissolve it in acetone, and then you evaporate the acetone, or at least part of it. I'm not very strong on the details of how this was done. This is how I understand it was done. But again, whether you get this pattern or not depends crucially on exactly how you do it. Okay, this is as I understand that it was prepared. But again, I didn't do this work myself. The experimental part of it, at least. Okay, so what I wanted to tell you is that under certain preparation conditions, what you get is this. And can I invite you to acknowledge that this looks rather like what's known as a wet 2D foam. Why is this a wet 2D foam? Because you have regions of liquid there in between bubbles. And how do we know that these are bubbles? Well, you can't see it very well on this picture, but in fact there are slight, if you take pictures at a higher resolution, well, there are imperfections on the bottom glass plate, like scratches and things that you can actually see through the bubble. And if you rotate it under your microscope, you can see them move. So it looks like there's air in here, which was probably trapped when the top plate was put on top of the film. And the fun thing here, of course, is that we have these bright walls, and we can look at them in a little more detail. They actually look like that if you blow them up. So, well, I think this is rather pretty. So you have the 2 small bubbles in there inside what in foam parlance is known as a plateau border. Here you have a 4-sided small bubble in there, 5-sided, another 5-sided one, and you have a lot of optical activity going on inside the walls and at these junctions, which means you surely have lots of defects in there. Yes, Oleg?
When you say optical activity, do you mean just birefringence, meaning optical anisotropy, or twist of the polarization of light?
We just don't know. What we know is this is between crossed polars, and this is what we see. There is something clearly non-trivial happening here.
So it's most probably birefringence.
Probably. I'd say there's some fairly complex defect structures in there doing things to light. Right, so, well, all this looks rather pretty, but, yeah, so what? Where do we go from here? So we decided to just wait and see. What does this foam do? So we have some complicated system. Basically, we don't have a clue what's happening in there. So let's just look and see what it does. And because it looks like a foam, this prompts the question, does it behave like an ordinary soap foam? Because there's lots of qualitative and quantitative results that are known for ordinary soap foams, namely how they coarsen, how they age. Basically, if you make a foam, like when you're washing your face or in the morning, and you end up with some laid at the bottom of your sink, first it is very white, and then gradually it goes less and less white, more and more transparent, and it also starts to disappear. The foam is intrinsically non-equilibrium, it will disappear, but before it does, the bubbles tend to get bigger and bigger. This is what's known as coarsening. It's due to basically to the air diffusion between bubbles. And all this can be made quantitative. So what we decided to do was, we haven't got a clue what's happening here, but how foam-like is this thing that looks like a foam? Does it obey known results for liquid foams? Right, but first let's look at a movie of what it does. So I'll now try and get the movie running. I'm not very sophisticated, so I still don't know how to put a movie inside the presentation, but hopefully it will run outside the presentation. Hello? How do I make this bigger? Over there in the corner, I think. Yes. Hello? Well, it worked a moment ago. There's nothing here. Is it running?
No.
It's not. It's not doing anything.
Dat me zetten.
But
Wil me zetten, waarom?
there was an arrow. Where's the oh, here. Here's the arrow. Here.
Yes.
Hello? Doing something wrong or failing to do something right, because a moment ago it worked. Let's try again. Here it is. Honest, I checked it a moment ago and it was working. Yeah. Well, this doesn't look terribly promising.
Yeah.
Just tell us what you saw.
Well, basically what you're going to see, but the fun is in actually watching it, is you see the bubbles grow. Escape? No.
Ja, ik ben
Can you help me out here? It got stuck somehow. Oh, I wrecked the thing, didn't I? Ah, Thank you. Thank you. Yes, here we go. Here we go. Yes, it's moving. Okay, so this is early times. At first, not very much is happening. I'll go away. Go away. At first, not very much is happening. This is frames taken first every 2 minutes, then every 10 minutes. But you can begin to see, well, it moves slightly. Okay, but you don't see very much. And now you see that it got noticeably drier. Not very much happens. This one's going to disappear. You see it's shrinking smaller and smaller. Off. There you go. This one's also going to disappear. So this, and now this is when the student went home for the evening and came back the next morning. So now every 10 minutes again. That one there, oh, it's gone before I could say it. This one's going to go as well. And that one's going to go as well. So now we have a very dry foam. You see very thin walls and virtually point-like plateau borders. These threefold vertices you see there, that one's going to go as well. This is what's called the T2 topological transformation, is where a bubble disappears. You also see T1 topological transformations, which is when bubbles switch neighbors. First you have two bubbles that are not neighbors, and then the edge separating the two that are neighbors shrink, so that two that were not neighbors become neighbors, and two that were previously neighbors become non-neighbors. I think that one's going to go as well. No, I think it's stopped now. Okay, it's stopped now, so we've reached the latest time that this went, but that bubble, which is five-sided, had we waited a little longer, as well as that one, would also have disappeared. Right, so now we exit this, and we try and be a little more quantitative. Oops, that's gone. What have I done? What have I done now? Well, let's go back. Yes. Control L. Let's try that. Control L. Control L. Oh, brilliant, thank you. And now we have to move forward again to where I was. Yes, so show movie now. So what next? Well, T1 topological transformation, as I've just described. So you see one edge shrinks, and for a very short time you have an unstable fourfold vertex there. This is extremely difficult to see in an ordinary liquid foam. They're very short-lived. Here, perhaps because the material is a lot more viscous than ordinary soap, what we have is one that we could actually catch on tape or on pixels, if we may call it so. And 10 minutes later, this vertex has split up into two threefold vertices that you see there. So previously, these bubbles, the top bubble and the bottom bubble, were neighbors. Now there's been a neighbor switch, and now it's the right-hand side and the right-hand side and the left-hand side ones that are neighbors. That's a T1 topological transformation, and because the time between these two pictures is 10 minutes, well, we can put an upper bound on the lifetime of this unstable vertex. Let's look at the T2 next. Well, you saw a few of them in the movie, but here it is. You have I think it's a four-sided bubble there, and now it's gone. You don't see it anymore. And there are many other such cases there. Again, this transformation took at most 10 minutes.
This is 10 minutes because you are evaporating under certain conditions.
Well, yeah. There's a lot of things happening here that are not fully controlled. For instance, you notice that those early time pictures showed a lot of fluid. The plateau borders were very thick. And then, well, oops, where is it gone? Now the foam is much drier. And what happens is it drains to the edges of the microscope slides. And, well, it will evaporate a bit, of course. It will also evaporate, but I think the main effect here is that the fluid drains to the edges of the microscope slide, so the foam basically dries. I'm sorry?
Coffee ring effect.
Yes, some such effect. Okay, so what else do we see here? Okay, let's try and be a little more quantitative now. What is known from ordinary soap foams? Well, a number of results are known. One of them is that you only, in a dry foam, that is one with small plateau borders, like what you see here, where your plateau borders are basically points, you have only threefold vertices, or your n-fold vertices for n greater than 3 are very short-lived, and the angles between films meeting at a vertex should be 120 degrees. This follows just from balancing surface tensions. Okay, so we decided to check, is this true? Now, I've had to split my results into 2 plots because, as I said, at some point our student went home for the evening. So this is before she went home for the evening, and this is after she came back the next day. Right, and that dashed line there is 120 degrees, again there, and these are results for bubbles with different numbers of sides. That's 4 sides, 3 sides, that's 4, 5, 6, 7, 8, and 9 sides. So what we did was we had to do some image analysis on those patterns we showed you. Let me just go briefly to one of them. Basically, in 2D, the films between bubbles are arcs of circle. We fit arcs of circles, and we measure the angles between them at the points where they meet. And if you want to find the size of a bubble, for instance, well, first you enclose a bubble inside such arcs of circle, and then you count how many pixels are there. This is basically how it's done. Of course, if you have a very wet foam, you can't do it, because then you can't really fit arcs of circle. Well, the angles at which they meet will be ill-defined. So you can really only do this for bubbles that have well-defined angles at their vertices, which means that your statistics gets degraded a bit. There's lots of bubbles you have to throw away. At early times, your statistics is not very good because there's lots of wetness in the system. At late times, your statistics won't be very good because there'll be very few bubbles left. Okay, so there's some limitations to this, leading to those rather large error bars there. But we are reasonably satisfied that they cluster around 120 degrees, which I think is telling us that the surface tension is reasonably uniform here. This need not be the case. It could not be uniform. In that case, there would be no reason why the angles would be 120 degrees. And the process appears reasonably quasi-static too, for the same reason. So what we have now, distribution of cell sides. So we're looking at how many sides, how many cells, how many bubbles of how many sides at different times, again, early and late. So a few words on this. Again, for each of these plots, time grows from left to right. So the black bars there correspond to the time we started our statistics, which we take to be arbitrarily time 0. And the rightmost bar, that corresponds to the latest of the early times. Same thing here. Black is the earliest of the late times, and this magenta bar is the latest of the late times. So what do we see? At early times, first you have bubbles with fairly large numbers of sides, 8s and 9s, and also you have a fair number of 4s. The number of 4s goes down dramatically. The number of 8s is still fairly high, even at the latest of the early times, and same goes for the 9s. There's a small but persistent cohort of bubbles with these large numbers of sides. At the late times, the 8s and the 9s are all gone. The 4s are still there, but decreasing. And what we see is that the foam is being enriched in 6s, 5s, and 7s. And again, this is qualitatively what you get in a liquid foam. It depends, the exact shape of this distribution depends slightly on the method of preparation of your foam, but in pretty much all foams what you have is mostly 6s and also lots of 5s, as you see there, and of course if you have 5s you've got to have 7s for topological reasons. Right, so distribution of cell sides becomes picked at 6 early times and n late times with relatively small, well, close to 6 again with relatively small errors. And as I said, the overall shape of the distribution and peak position agree generally with those for ordinary liquid foams. Now, what else do we have here? This is a quiescent foam. I didn't say that explicitly, but what this means is you make the foam and you allow it to do its own thing. You don't do anything else to it, you just look what it's doing. At a later stage, we'll do slightly nastier things to our foam. Okay, now what we're looking at is we're trying to tease out a growth law for our bubbles. Now, it is known for ordinary liquid foams that at late times, the mean bubble area of an ordinary 2D liquid foam should grow linearly with time. In LC foams, liquid crystal foams, at the time we published our work, it was not clear what the growth law was. One might expect that the same result would carry over, but I found one result, not in any published journal, but in an archive preprint, which claimed that it should be a smaller exponent, something like 0.4, and this would be due to interactions between defects in the foam slowing down its coarsening. Well, what happens in our case is that, frankly, our statistics isn't good enough to tell one way or the other. Subsequently, there's been a more detailed work also involving a smectic foam, which confirms that the exponent should be 1, and this discrepancy with the earlier work might be due to the fact that here they were using an extremely wet foam, whereas the scaling regime corresponds to very dry foams. That may be the source of the difference. Right, so what we could conclude at the time is that our data were not incompatible with a linear increase of mean cell area, but they're not incompatible with other possibilities either. We just don't have good enough statistics to tell. Now, Lewis's law. Lewis's law is something very popular with people who study foams, and basically there's two laws calling, there's Lewis's law basically tells you that large bubbles have more sides. But what does large bubbles means? Well, in Lewis's parlance, large means larger area. And what Lewis's law tells you is that this was an empirical law. Lewis was a botanist, and he discovered this empirical law when looking at vegetable cell tissues. And what he concluded was that the mean cell area should grow with number of sides linearly. Should grow linearly with its number of sides. Now, this is one way to define a large cell. It's one with a larger area. Now, there's another version of this result called Desch's law, which tells you that a large cell is one with a large perimeter, and it's the perimeter that goes linearly with n rather than the area. Well, each of these laws have their supporters and their detractors. Various cellular patterns obey either one or the other more closely. I think Lewis's law is marginally more popular with people working on liquid foams. And here I again plot the mean area of cells of a given number of sides versus n at the earlier times and at the late times. And I'm afraid the only thing that we are able to conclude here is that, well, agreement with Lewis's law is at least as bad as in ordinary liquid crystal foams. So again, in this respect, our foam looks like, in ordinary soap foams. So again, in this respect, our liquid crystal foam appears to behave like an ordinary soap foam. So, well, you can try and see a linear relationship there, but frankly, it's just 3 points. It's just point n5, n6, and then 7. And again, there's a clear concavity, there's a clear upturn there, which again you see if you do this kind of statistics for ordinary soap foams. So let's move on. Now this is nice. Something called von Neumann's law. Von Neumann's law tells you that cells with more than 6 sides should grow. Cells with fewer than 6 sides should shrink. Cells with exactly 6 sides should stay the same. So now we use only late time results. And you see again there's a lot of noise, but this green is for 6-sided cells. So that's mean cell area as a function of time. This is 6. This is 7. Sorry, this is 7. That's right. This is 6. This is red is 5, and I even managed to get out a few points for 3. So it's actually looking not too bad. So these stay about the same. These clearly increase in mean cell area. That's the 7s, whereas the 5s, and even more so the 4s, clearly go down. And if you plot this time derivative of the cell area versus n minus 6, indeed you get a straight line there with a fairly good agreement, I think. So this doesn't look too bad. I should emphasize here that what we've done here is what I would call the weak version of von Neumann's law. Von Neumann's law applies both to, at least in ordinary soap foam, it applies both to each individual cell and to the mean area of cells of a given number of sides. Now, verifying von Neumann's law for each individual cell requires that you track individual cells, which is a rather labor-intensive process which we were not able to carry out. So what we did was we verified the weak version of von Neumann's law, which applies to the mean area of cells of a given number of sides. And well, maybe it's lucky that we did so, because the later work that I just mentioned that confirmed the linear growth law for cell area claimed that von Neumann's law does not hold or may not hold for individual cells as a result of the cell walls being of non-uniform thickness, at least for the system that they used. I can't tell whether this would also be the case here. Probably not. Our cell walls appear of reasonably uniform thickness. I just don't know, but this is a possibility. Right, what else do we have? So all that I've described so far was for what we rather coyly call uncontrolled shear. That is, you just pressed the slide with your finger, you made a foam, and that was that. You just watched what it did. But then we decided to be, a little more fastidious and look what happens if you apply controlled shear, if you try and keep things a little more under control. You do controlled shear, you try to keep your film thickness constant throughout your experiment, you try to keep moisture out because, these are ionic fluids and they're also hygroscopic. They suck up moisture from the air, and they may even be amphotropic, that is, both thermotropic and lyotropic. This may or may not have been a factor in the results that we got, because, as I said, the original preparation was rather poorly controlled. It may be that the fact that we get asymmetric at room temperature results from shearing. It may also be a result of the system sucking up some moisture from the air and undergoing a lyotropic-like transition into some lamellar phase. So now this is a little different from what we did before. Before, results I showed you before, we were looking at long times while doing nothing to our foam. Now what we're doing is we're applying controlled shear, and we're looking at its effect on timescales much shorter. Now we are talking timescales of a few minutes, whereas before we were talking timescales of up to a day, or at least more than 1,000 minutes in all. So some details of what was done. Again, room temperature, but now well-defined shear rates. Sample thickness was 5 microns, sorry, now carefully controlled. And well, this is just the schematics of the experimental setup. This is the kind of thing you would see when looking under the microscope, and shear is applied using this rotating plate arrangement. Again, we look at our system under, well, not quite crossed polars. In fact, it was best to disalign them by about well, between 70 and 80 degrees for maximum brightness of our images. Right, so the first thing that we notice is if you start shearing your system, you need a minimum amount of shear to get a foam.
But Paulo, is the shear rate a function of radius?
Is the shear rate a function of radius?
Radial position up
Yeah.
in the center.
I'm not sure about that, Mark, but in any case, we observed always at the same distance from the center of rotation. So the shear rate is well defined. Okay, so now this doesn't show well at all. At this point, I wanted to show you a movie, but I have to admit that the movie fell victim to a hard disk crash at some point, and I wasn't able to retrieve it. So please believe me that there was a movie showing these images at some point, and what we see here is just a time sequence which is not very sharp, but you can see films there, and this time increases left to right and top to bottom, and you can see films here. And one of the results that I'm going to describe later is that now this is clearly non-equilibrium. Well, it's non-equilibrium because any foam is non-equilibrium, and now I've put it under shear. And one of the interesting features now is that your angles will in general not be 120 degrees. They'll be a little different, and how different they are will depend on whether your bubble is large or small, basically. Right, so a few more pictures. Okay, so these are snapshots of sheared ionic liquid crystal foam between polarizers for different shear rates. That's 70 hertz, that's 70, this is 100, that's 160, that's 200. So the most remarkable result, I think, is that you see the film breaking up into smaller and smaller bubbles as you increase the shear rate, and we'll quantify that in a moment. Still, you see that this has the usual foam-like appearance. You see a 4-sided bubble there, you see 5-sided, a 6-sided there, but now they tend to be a bit anisotropic. The shear is applied along the vertical direction, as it says there, and some of them appear to get elongated along the direction of shear, others appear to get compressed. Right, so first we look again at internal angles in a foam under shear. And what we find now, this is again the baseline, as it were, the 120 degree line. And now we find something, again we have very large errors. But what we find is that cells with fewer than 6 sides tend to have larger internal angles. So that's red is there, red is, which is 3 sides, is there, there, and there. The blue triangles, which are 5 sides, are there, and there. And again, this is data points for the 4 different shear rates that I showed you before. For large numbers of sides, say 9, we're down here. So smaller internal angles for the bubbles with more sides, which also tend to be bigger in a general sense of tending to be bigger the larger the number of sides. What else? Distribution of cell size. What do we see now? Well, again, this is now for different shear rates. Black is slowest and blue is fastest, so the shear rate increases from left to right, as I said. And well, we see a clear effect of the shear rate both on the shape of the distribution and on the mean number of sides of cells. But what we see now is that there is huge variability. The standard deviation of the mean number of sides is now quite large, much larger than for the quiescent foam that we saw before. Mean cell area size versus shear rate, and this is just quantifying what I told you before. What you saw in those pictures is that the faster you shear, the smaller your bubbles, and this is true for bubbles of all numbers of sizes and also for the mean area of all bubbles. That's the black dots. So there's a clear trend towards smaller cells at higher shear rates, which might be slightly non-monotonic. Might. Right, so this is it basically. So here are conclusions. We have attempted to quantify the morphology of our non-equilibrium liquid crystal foams, both quiescent and under controlled shear. And our results suggest that the system, as in the case of ordinary soap foam, may be surface tension dominated, despite the fact that it is a lot more viscous than most ordinary soap foams. There appears to be a threshold shear rate for foam-like patterns to form. And above this threshold, larger shear rates produce smaller cells. We don't know exactly what role liquid crystallinity is playing here, if any. We just don't know. Well, we may get a foam because we have a smectic, and a smectic basically is a soap. The fact that it is ionic probably does not play any role. Those other results from other people that I just mentioned were done for standard HCB thermotropic liquid crystal, and they're qualitatively the same. So the fact that this is an ionic liquid crystal is probably irrelevant. Many outstanding questions. These are just some of them. What's the effective temperature? The other group, incidentally, that's Stanarius in Germany, they looked a bit at the effective temperature. In particular, it changes the slope in it changes that constant in von Neumann's law, but von Neumann's law is still obeyed. It changes the slope of the line, but not the fact that it is a straight line. What's the effect of film thickness? What's the effect of water, residual water or atmospheric moisture? What is the true long-time dynamics? Because, well, we don't really have good statistics for that here. And another question is, can we stabilize it like it's done for ordinary foams, for instance, by adding solid particles? And there's a school of thought that likes to stabilize foams by adding talc powder to them. I tried to persuade my experimental colleagues to do this, but I wasn't very successful. So if any of you ever dabbles a bit in foam, try adding talc powder to it. Apparently it works. So results were published here. Thanks to the people who gave us money to do this. Thanks to you for listening. Thanks to the Isaac Newton Institute for allowing me to speak here. And mandatory shameless publicity plug as a last slide. Thank you.
Thank you, Paulo, very much for your contribution. You might pass me.
Yes.
Total dimensional your system.
Well, the microscope slide will be on the order of a centimeter across, and the thickness is on the order of, say, 10 microns.
In the law you shown the essential for two-dimensional
Yes,
and three-dimensional.
what I showed you is von Neumann's law for
It's
2D foams.
pure two-dimensional.
Yes, it's two. There is actually a huge debate over what is the correct von Neumann's law in 3D.
Yeah.
But no, we're treating it as a 2D foam. Of course, a 2D foam is never truly 2D, but what I mean is it's a bubble monolayer. Yes, Claudia?
Curiosity, you mentioned that HCB also gives
Yes.
similar results.
Yes.
But HCB, I think, has a fundamental difference is that it has a nematic phase.
Yes,
While
this
this
is
system do not have a nematic phase.
no, that's
Normally
right.
coming
Well,
from
the results that I mentioned by Stanarius are for HCB either in the smectic phase or, well, just slightly into the nematic phase if you start from the smectic and you heat it up just a few degrees. Because what they say that this is because, well, if you go just slightly, ever so slightly into the nematic phase, you still have some smectic layers, so you still have a foam. I'm just quoting from their paper.
This imidazolium salt normally have different types of smectic, don't they? They can have a rotator phase where they are kind of smectic or
Yes.
tilted. And you mentioned that you have to rotate your polarizer to get
Well,
them
we
to
had
balance.
to
That's
rotate them a bit to get better quality images,
So-
but
Could it be that you have a tilted smectic?
maybe I don't know.
Margherita?
Just how close do you get to the bilayer in the wheels, not the wheel, so foams and in these foams? When you look at the late stages, how
Yeah.
thin are your
Oh well.
molecular?
Well, as I said, here we did not control layer thickness. I don't know how it would vary, but I mean, here you were only looking at a small portion of your microscope slide, because I showed you this portion which is perhaps a couple of 100 microns across, whereas the actual slide is about a centimeter. In experiments on soap foams, the so-called monolayers, well, it will depend on how big you want your bubbles to be. Typically, they'll be on the order of a few millimeters across. So that's the thickness of your monolayer in an experiment, a typical experiment involving soap foam. I mean, here, I don't think, well, I can't be sure of this, but I wouldn't have expected the thickness to have varied by more than a factor of 2 or something. But I don't know.
The wall,
Sorry?
when you have the bilayer in the wall, you have a bilayer of soap.
The walls between bubbles. The walls between bubbles and the plateau borders. Well, they're on the order of a micron across. So that's a lot of smectic layers.
Much more than a bilayer.
Oh yes.
So
It
like an ordinary foam.
An ordinary foam. Well, again, it depends how wet it is. A Newton black film could be on the order of tens of nanometers or something like that. A Newton common film is much thicker than that, on the order of maybe microns.
Just out of curiosity, wouldn't it make sense, or have you looked at the dynamics of the joints? I mean, if you have a triple junction
yeah.
or a higher order junction, do they have different dynamics? Or is it something that would be interesting?
Well, as you saw, again, you can only define junctions in fairly dry foams. And in the because otherwise your plateau border is just a big blob of liquid. Okay. And most junctions you see are threefold junctions because all others are unstable. They will have a finite but relatively short lifetime. We did not look at that quantitatively.
Because by comparison with the theory of polycrystals,
Yeah.
where evolution of polycrystals is
Yeah.
basically modeled by the evolution of crystals.
Okay.
So there is some similarity.
Okay. Okay. Yeah. Well, you find this kind of pattern in polydomain crystals. You find them in various types of granular materials. It is a quite common, at least visual similarity. Even if sometimes the underlying mechanisms can be a bit different.
Yes, there's still time. We have to.
Again, when you spoke of the effect of shear,
Yeah.
I think one possibility is the first effect is of changing the orientation of the smectic with respect to the surface. I think in other ionic, if you prepare your sample between a cross polarizer, you shear
Yeah.
black, because normally they
Yes.
tend to align
Yes.
perpendicular.
Yes. They
By
are
shearing the
homeotropic.
slide,
Yeah.
by shearing the slide, you start to see textures because you're changing the orientation from perpendicular.
From perpendicular. Again, it is quite possible. It is quite possible. Sadly, at some point, this student decided to leave, so my friends were not able to pursue this work much further because, well, there's clearly lots here that deserves investigation. What you just said, both concerning anchoring at the surface and concerning exactly what type of smectic that is, and, well, many others. But yeah, sadly we were not able to pursue this. Well, if any of you,
Cruz is Carlos Cruz. Is
that's
NMR.
right. Yeah, that's right.
So he could actually do the NMR experiment if you iterate it.
Any further questions? We'll have a wild idea more than a question.
Yeah.
Because just to describe on forms this, the degree of order.
Yeah.
One could say, suppose I take a patch, say a circular patch,
Yes.
and I take the average of all sides that are on that of the cells
Uh-huh.
that are on that patch, and in such a way we could construct a kind of shape order tensor
Yes.
uniformly defined on. Has this
Yes.
been attempted?
Yeah, we did something like
you
that
did.
for clusters some time ago. It goes a little beyond what I wanted to tell you here, but we can discuss that later. Not
Right.
for liquid crystal foam, but for ordinary foam.
All right.
Yes,
This
they
is a
do.
general idea.
Yeah, they have a P2 order parameter as well.
Oh, so it was not that wide.
Ordinary foam, not liquid crystal foam. The clusters are not isotropic. They have a P2 order parameter.
Well, thank you, Paolo, and for your contribution.